And now I'm going to clap them again for the lights to come back on in just a moment. Now, these are commands that are done in advanced homes where you've got the Internet of Things that takes over commands for things like electricity. But think about more basic human tasks that you carry out. Think about your young child in your house that you ask to get you something. For example, spray the house with insecticide at 7 p.m. That's a task. That is data. You could also say, tune in to Arise News at 8 a.m. to watch the morning show or the Global Business Report at 11 a.m. Or you could say, hey, my dry cleaning is back. Hang my clothes at a particular place. Every single task that you carry out in your home is data that is being fed into a large language model that is used for the development of humanoid robots. There is a company in Norway called 1X Technologies, 1X for short, and they are developing humanoid robots to carry out tasks in the home. It is crucial that the data that human beings, or rather I say data, the tasks that human beings carry out on a daily basis is collected and fed to these machines in order for them to be able to take over tasks in the future. Ladies and gentlemen, this is not to be laughed at. The future is here, and this company is getting ready to deploy these humanoid robots as soon as 2025. S3 Technologies put this together. Let's take a look at this deep dive into humanoid robots from 1X.
1X has been building robots in Norway since 2014, developing their own tendon drive technology as well as their first robotic system, Eve, a humanoid-like robot with a wheel system for ground movement and parallel grippers for hands. But now, 1X believes they're not only ready to build a humanoid robot, but manufacture them and deliver them to paying customers for use in their homes as soon as next year. I drove from our studio in San Francisco south to Sunnyvale to meet NEO for the first time and ask their team more about how they plan to bring humanoid robots to the home.
My name's Bernd. I'm the CEO and founder of 1X, and we make humanoid robots for the home. It's the cliche, but I knew I was going to do this since I was a kid. Kind of kid that had like his cabinet full of stuff that I picked apart, putting it back together. For some reason one day while like looking at an excavator, doing work, and like, okay, I'm gonna make humanoid robots. That's what I'm gonna do in life. I think I was like 11 or something. This is just reshaping the world in our view. So this is our Bay Area office, where we have our AI team. Main office is over in Norway, where we do all of our manufacturing development and production, hardware engineering.
So here at the manufacturing operations and engineering department at 1X, we have a very diverse team. There are people who are responsible for designing the processes. We have a very strong quality team as well that support that system.
And we create robots that are safe, capable, and affordable. So we can create robots that can live and learn among us. A lot of like early inspiration from Honda Asimo. I think it was like so ahead of its time and kind of still almost is, right? And followed the field ever since.
I've always been interested in robotics and AI. So as a small kid, my favorite movie was The Iron Giant. That was not a compliant robot, by the way. A compliant robot is a safe and soft robot. The Iron Giant was very large, very stiff, and very dangerous. So I had the fortune of being able to join the Google Robotics Lab really early in 2016, where I spent 6 years at Google Brain studying how to make general purpose robots learn tasks. I came to the realization that the algorithms really would scale. The deep learning really was the right way to solve robotics. However, the limitation was the hardware. In order to really get to the millions of tasks, you needed a hardware form factor that was safe enough for the home and also could reach everywhere a human body could reach. And the most obvious form factor for that is a human body. Around 2022, I met Bernd, and we realized that if we could merge the compliant humanoid form factor with a very general purpose AI strategy, that could solve lots of tasks and allow us to push into general purpose unstructured environments like the home.
So in 2015, we focused on the foundation technology, building the motors. Then 2016, we had the first full two-armed robot that could do some stuff, allowing us to raise some external capital and start scaling. 2018, first full Eve. 2020 was all about commercializing Eve, starting to run pilots. 2022, we launched Eve 2, where we did the first actual commercial rollouts with real customers. And now for 2024, we're transitioning over into Neo, which is going to be the first robot where we can fully go into the homes. For the last 9 years, we've really been going deep down the rabbit hole of how to design and manufacture every single component that makes us able to create systems that are closer to human. So the only way we get truly intelligent robots is to get them into them. Think about early LLMs, right? There was a lot of people thinking like, oh, we're going to train very narrow wedge approaches, where if you train on exactly the data for the task that you want to apply this to, this will create the best model. Now, this clearly proved out to be wrong. So the only way you get to truly intelligent systems is in the home, where you have this enormous amount of diversity. I think that's how we learn, right? We learn by experimentation and observation, not just through observation.
We collect a large, diverse set of robot data with our humanoids, both Eve and Neo. We train a robotic foundation model that captures all kinds of knowledge about the world. And then we turn that into a helpful assistant using the same techniques that have been shown to be very helpful in language modeling.
So this is Eve, which is our first product. Eve's about 4 years old now, and this is the first generation of all of our technology. So all of these early innovations that we had to do to be able to create systems that are like compliant, backdrivable, safe, strong, and able to interact with the world to learn, even in our spaces, really started here. This is what now is getting matured into the second generation of the hardware, which is in Neo, and where we really feel we can take the final step to be in all of these diverse environments that we have at home, to be able to truly learn among people. It's all about making sure that there's as little energy in the system as possible. So if you think about these classical robotic systems, they're often driven by very heavy, very high gear ratios. Inside, there's nothing really that's moving any faster than what you can see like the body itself move. What in a normal classical industrial robotic system, you would have like a motor and a gear inside here, typically spinning 100 times faster than the arm is moving. Now you have to take that 100 times and you have to square it. So now you have a multiplier of 10,000 on the energy of that system. And all of this energy has to go somewhere when you instantly have to stop. It's all about building systems that are passively safe. And like we humans, we don't think about this, right? But if we run around a corner, we bump into each other, it's not really dangerous. For most robots, it's roughly similar to holding a 15-kilogram kettlebell in your hand while moving. So now you can think about like, okay, if I have a 15-kilogram kettlebell strapped to each of my wrists, and for the legs, it's usually like 25 kilograms. And you see this in how robots typically move. Like when you see a robot walk and it's walking like this, actually you would walk the same if you had a 25-kilogram kettlebell strapped to your foot. Because now you need to be very careful, right? Very soft. This is also inherently just extremely unsafe. This worked extremely well in robotics for factories. When you're in a factory, everything is calibrated, so you can move very fast, very precise. And whenever you're going to touch something, you can slow down, right? And this is because there's so much energy in the system that if you collide it, that will go really bad. And generally in robotics, right, you call any kind of contact with the world, we call it a collision, which is starting with the wrong approach to the problem. Everything we do as humans in everyday life is colliding. Like whenever we're taking a step, we're colliding. Or picking something up, we're colliding. It's very hard to know if like, am I supposed to touch this or was it an accident? So you really need to build into your system how to minimize this energy so that you're just inherently safe. You can't trust your sensors on this. And that just requires a completely different approach to robotics. So what's pretty unique about this is kind of like just like for us humans, we have the motors up here with the tendons that are pulling, very similar to muscle. And this actually allows you to, for example, have two motors here together drive the 2 degrees of freedom here. So just like for me, when I'm doing this and I'm doing this, it's the same muscles. So you don't have to carry as much muscle to have all this flexibility. And that's the same here. So you can see like this, it's the same. Due to having this bio-inspired approach to the joints, where your very low ratio strong motors are pulling the tendons, you get this very compliant, safe nature.
From a software perspective, manipulating bits is very simple, right? If you say copy this file from A to B, it'll very likely show up in B when you do the copy operation, because computers are made very reliable. If you contrast this with robotics, if you ask a robot to flip on a light switch, you don't know if it even touched the switch. You don't know if the switch turned on. You don't know if it fell over in the process of trying to turn on the light switch. If just basic sort of operations that robots are asked to do are hard to measure because you don't really know the state of the world outside of the robot. So I would say that the main difference between manipulating the physical world and manipulating the digital world is that you only have control over really what's inside of your robot. Once your robots are much more intelligent, you can start to imagine that they become much more reliable at manipulating simple things in the world. Like maybe in a few years, we can take for granted that robots can pick up objects and deposit them in some other location with extremely high reliability. And that's kind of like being able to copy a file from one location to another in your computer. But again, like to solve general purpose labor, you need the operations that robots perform to be much more reliable than that. And we hope that in the limit, when robots are as intelligent as humans, you can think about the entire physical world as a sort of computer where you can move things around just as reliably as you might move something over the internet. To solve the large diversity of tasks that you encounter in the home, you need a lot of data that captures all this diversity. This is the same approach that has underpinned technology like ChatGPT, where you need data across many different types of tasks. Not only do you need those tasks, you actually need even broader set of things like things from the internet and so forth, right? So the analogy in the home might be you want robots interacting with objects in all kinds of ways, both useful and non-useful. Once you have all that data, you can try to compress that knowledge into a very powerful model that generally understands the structure of that data. In language modeling, this is achieved by basically predicting the next word. And you can think analogously, if you're able to transform robot data into a similar format, you can also predict what comes next as a way to distill the intelligence about the data in the world into a single model. You basically take data around, is this good or is this bad? And you align the model to be generally generating good behaviors rather than arbitrary behaviors. And so that's the basic approach we're taking at the 1X AI team. Our approach to data at 1X is fairly straightforward. We collect data from the environments that we want to deploy the robots in. I do think that there's many approaches to building a general purpose robot and finding sources of large amounts of data. This can come from the internet, this can come from human videos, this can come from simulation. But at the end of the day, you're going to deploy this in a home and you need some amount of data in the home. So there's no way getting around that. We're just going straight to that approach, and we're trying to not be too clever with the data collection, and we're just scaling up the thing that we know is in the test set. And once we have the data that's very closely aligned with the deployment setting, we're pretty sure that that data is high quality enough that we can train things to work in those environments. I think the data we've collected on Eve captures a very large distribution of scenarios you might encounter in the real world. But we get this question a lot, actually, about whether we're going to use Eve data for Neo. I do think that in practice, over the next 12 months, that data will become increasingly less and less important. Again, it's one of those, a lot of people try to overthink the data collection problem. We think that we've built enough experience operationalizing how we collect data that we could pretty quickly catch up the diversity and scale of the data we've collected on Eve pretty quickly on Neo within the matter of weeks. So from an engineering perspective, it might not even be worth the time to port the Eve data to the Neo data.
Go to Westwood.
So what we have here is a policy that our Android Studio team member, Brian, trained by himself.
Open door. Go to toilet.
This is not produced by the AI team, but rather a capability that was learned using only data collection and a no-code interface that we built here.
Lower seat. Leave restaurant.
There you have it. That's some of the autonomous capabilities we're training on Eve, and we'll be bringing those to Neo very shortly. You can see there when it was leaving the door, it bumped into the door, but that's totally fine because the compliance of the robot really is making sure that we're designing these robots to come into contact with the world, even accidentally sometimes, which it will happen.
Building humanoid robots is a really interesting problem because none of the components that you really need to build this exists. So when we say that we manufacture this internally and we have a very deep vertical integration, we mean all the way down to we coil our own coils for our motors, and we literally get copper and aluminum in, and we get droids coming out of the factory. And controlling your own supply chain has been incredibly important to be able to kind of control your own destiny as you scale this.
We start first by ensuring that we have a robust process for the assembly of the core components. So these would be, for example, our actuators, the motors, and the different components of the drive units. Once we finish these, we would move to the next stage where we build up the sub-assemblies that embody the different parts of the robot. And when all these sub-assemblies are finished and tested, then we put the final robot together, and then we do a final verification test that it works according to its specifications.
For Eve, we last year peaked out about between 10 and 20 units per month, manufacturing-wise. For Neo, we're going to do 5 to 10x of this in the factory we're building right now. And luckily enough, we have all of the experience from the hard work of manufacturing Eve and getting that into the market. Even though the system on the surface might look more complicated, since it's the second generation of our technology, manufacturing-wise, it's actually quite a bit more efficient to assemble and manufacture.
I think working at the intersection of AI and robotics is really cool because it is the mix of a job that is both challenging intellectually and fun. Like just like when you see the robot actually start to walk, everyone claps and cheers, right? It's really exciting to see it kind of get to a working state. This is like a perfect career, I think, for people who are interested in having a big impact on the world, but also working on challenging problems. And it's really hard to find actually jobs in the world that have all three of these things.
It's all the cliches, right? Like founding a company and like building it, you realize all the cliches are true. It's about grit. Everyone will tell you you're wrong. Everyone will laugh at you. I think the biggest thing you can do as a founder is to have conviction in your own idea. If I look at like companies dying, also in robotics, it's often because they had this like great intuition about like, this is the thing we should do. And then it gets watered out because people just keep beating on them. And you're like for us, right? Oh, you can't use tendons to drive a robot. They don't have reliability, durability, all of these things. That's been tried many times before. And then try again. And you try again for years, and you finally make it work. And I think that's the true innovation, right? It's a cliche because it's true. Just like, don't give up.
The next major milestone for 1X is to take all the learnings we've had on AI and foundation models in robotics from our fleet of Eves and transfer it to Neo and deploy this in the home. So this is another level of difficulty from what we've experienced so far, because when you're deploying robots in the home, you don't have the ability to test new ideas at customer sites. They really just have to work on day one. So as a technologist, I'm super excited about the possibility that the physical world becomes a computer. This would basically be a huge economic unlock in the amount of productivity we can do. Of course, there's also the benefits to the aging demographics, and I think this kind of technology is really essential for the survival of the species if we're going to keep growing the size of the population and keep a high standard of living for everyone on the planet. And then also it's just extremely amusing to see robots struggling and also succeeding. I think that really inspires me when the robots actually can do something smart.
So 2025 will be the year of scaling this. 2026 is kind of like still early adopter, scaling manufacturing, gathering all the data to make the systems intelligent enough to be really, really genuinely useful. 2027 is probably where we start to see that the systems are intelligent enough that we can apply them to other domains. So going into everything from like manufacturing to service industry, warehouses. I think at that point you've hit kind of the sweet spot where these affordable systems are useful enough that the unit economics are just crazy. And you're going to be severely bottlenecked by how quickly can you manufacture this. 2027, 2028, 2029, 2030, it's going to be all about manufacturing at scale. And how do we get to billions of droids? We're figuring out how to process this right now. But what I can say is that we can manufacture this at a cost of a relatively affordable car. And then I'm not talking about a car that someone in Silicon Valley would buy.
Incredible stuff. And it is at our doorstep starting in 2025. Incredible work there from 1X, located in, headquartered in Norway, but of course doing their work also in Silicon Valley.